Here he's going to talk about caves. He's a very famous, I guess, I don't know this world, but this field, cave explorer. He's been responsible for discovery and exploration of many caves, which he will cover, and he will have pictures, much better than what I can do. He's also is being involved a lot in aerospace and underwater exploration as well, which ties into the cave. And I'm doing a terrible job of introduction, so I'm going to let him talk about this himself. But remember, there is the 12:30 talk, which should be also a fascinating one. Thanks.
Okay, I want to thank all of you for the opportunity to come out here. This is for me a rather eye-opening experience to see what Silicon Valley has metamorphosed into over the last 10, 15 years or so. I used to do some research work in collaboration with Ames. I've met a few of the people who have migrated here from there. As the interest in the space arena change over time. I've had the privilege over the past 25 years of being involved not only with space exploration related projects, aerospace vehicle design and things like that at a national lab, but also of leading some projects that deal with some of the last untouched, truly unexplored terrain that exists on this planet. If you try to ask yourself where would you go if you really wanted to go someplace that was truly unexplored, you think about the mountains, right? I've climbed some fairly high altitude peaks. You can get satellite images of where you're going while you're on the mountain. You can call up people through sat phone. You can get weather forecasts for the next day to try to plan your summit assault. That's how much the alpine environment has changed over the last 50 years. Similarly, with pretty much all of the tropical rainforests, the jungles, and the other places, the arid deserts and things like that, as well as underwater. Some may argue that the ocean is one of the least explored places, at least when you get down to talking about touching every square meter. That's quite true. But as far as knowledge, we have really detailed benthic maps of the entire floor of the ocean. We visited the deepest spots, and pretty much like the plans to return to the moon in 2020, people were talking still about returning to the bottom of the Marianas Trench as if it were a big deal. We ought to be able to do better than that. But in one particular area, and this is something that's taken me a long time to realize, what constitutes a true frontier, right? It's a place where, in my opinion, the exploration consists of a process. And this is where many people try to wiggle out of the definition. To me, the definition of exploration is putting this in terra incognita, nothing short of that. Now, you can do it in many ways by gaining scientific knowledge by using intelligent mechanical surrogates. Now, we call these things robotic spacecraft, for example, or robotic autonomous underwater vehicles. And the question then becomes a philosophical one. Is it better to see a raster line appear on a television screen of the image of a place that no one's seen before, or is it better to be there in person, to be able to look at it and interactively touch it, feel it, experiment with it, observe, satisfy the curiosity of the human species? I tend to fall into the latter category, but there are places where indeed it is too dangerous, too far, simply because our limited knowledge of propulsion has not allowed us to get there more easily, or perhaps it is in fact a lethal environment. Like, for example, the surface of Europa is not a good place for humans. 5 minutes there and you would have a lethal dose of radiation, largely whipped up by particles from the sun going out and being spun up in the gravitational sphere of Jupiter. So what I'm going to talk about here now, and I hope a couple of you will find your way over to the talk at 12:30 on Europa, because there's a lot of cool stuff that's going on in the robotic area, as well as many of those in California who have had any association with JPL or Ames would know. But this is about what's left on Earth, and it has to do with the exploration of extraordinarily deep caves. Everybody's probably at one time or another visited a commercial cave. What I'd like to show you today is a very unknown world, or at least unknown to almost everybody I know, except for a very small band of expeditionary groups that are around the world who do know what's going on and realize that this is in fact a finite, dwindling frontier, and they're going for it now on expeditions pretty much as 2 to 3 or 4 months a year until they run out of time. So what I'm going to show you is where things are happening. There are largely 3 places in the world right now where there is a competition going on, for lack of a better term, between good-willed groups. Russians are leading one in an area of Chechnya, which is a bad place for Americans to go, unfortunately. The U.S. is leading a multinational team of about 10 countries to an area in southern Mexico, and there are pockets of work that are taking place at high altitude in Austria and the French-Spanish border and places like that. But largely, it is shaking out now to what we would call the 2,000-meter plus game. The deepest caves in the world for the longest times were measured as a crossing of 1,000 meters, much in the same measure as you would consider a high altitude peak to be an 8,000-meter peak. And there was this gradual push to where things slowly grew towards 2,000 meters deep. It was as much of a physical barrier as a psychological barrier to think about it. And I hope when you see these slides here, you'll get a feel for the fact that these are not, it's not like going to a national park. These are projects where to gear up is equally or greater than the logistics involved with the largest Everest expeditions that were ever put together. Typically, you're looking at a 50-person team on site for 4 months. It takes on the order of 2 to 3 weeks to get your team to base camp. It takes several weeks to initially begin to prepare a place like this for travel, and you'll kind of see what that travel is like. And then there are a whole host of obstacles, at least 3 or 4 or 5, that I would run into the category of extreme situations where we have had to invent technology. And we've been doing this now for over 25 years, and you'll get to see some of that here. The place that we're working, the U.S. team is leading, is in southern Mexico. If anybody's been down there, it's about 400 kilometers southeast of Mexico City in the northeastern tip of the state of Oaxaca. The idea is that there is a large entrance up there called Cueva Cheve, which was discovered about 20 years ago. And at that time, it was explored down for a certain distance. The water that goes in these things, unlike a Jules Verne journey, does not go to the center of the Earth. They go towards the center of the Earth, but eventually, with most of the deep cave systems on the Earth, they have to find a way for the water that creates them. These are created in limestone. There are, in fact, lava-type systems, but they don't go as deep, at least not yet. Most of them collapse because of the hydrostatic pressure. In this particular case, in Cueva Cheve, we have the possibility of hitting over 2,600 meters down over a distance of about 20 kilometers. And the waters come out in a spring down here in the depths of this place called the Santo Domingo Canyon. So those are kind of the topograph places that are going on, and we have projects that are going up and down this mountain range. It's about 20 kilometers from left to right, about 6 kilometers across, and 2,600 meters deep. The game then is what's in between in the center of this mountain, and how deep can you go in it? Yeah?
How do you define the depth of a cave?
It's the vertical extent. I'll show you here at the end. In order to determine that, you actually have to survey what you're doing inside the mountain. So we actually have a 3-dimensional computer model of the inside of the mountain that I'll show you right at the end here that shows where everything sits inside. If you go from point to point, for example, if you go from the highest known point and you pop out in the resurgence springs, you can go down there with phase differential GPS, and within a centimeter, you know exactly what the vertical differential is. So when we talk about depth, it's the vertical differential from the highest point to the lowest point. If you're talking about the length of a system, that's an entirely different animal. The stuff that's being found here will probably, when it all winds up, be in excess of 150 or 200 kilometers worth of passages that weave their way in through the interior of this mountain. To do that, however, is going to be a logistical challenge, the likes of which we've really not dealt with yet here on Earth, and I'll tell you why. It's kind of a dramatic statement to make, but when you see what we've gone through to get the knowledge that we have and what remains, you'll see that it is in fact logistics that control the entire thing. So basically, you can start many projects here by trying to choose a target point to find your way inside the mountain. This one here is at the bottom of a canyon that is deeper than the Grand Canyon. It's called the Santo Domingo. That's just a part of the ramparts of the plateaus surrounding each side. They go up over 3,000 meters in each direction. This is typical type of morphology that you find down there. You're going in through fairly dry type stuff. Because you're at a resurgence spring, you're working upwards through the mountain. These are some local Mexicans from one of the village. Just like in the U.S., you might have farmers that would own a cave down here. They're Mexican ranchers. these are the kinds of things that people typically think about when they think about caves. They're relatively small. They have formations in them. This is what you would find if you went to a typical tourist type cavern. When you get further in, you find out that you're dealing with places that are flushed by seasonal rains. And this is one of the controlling factors in southern Mexico, is that you really only have about a 4-month window between the beginning of February and the end of May when you can conduct any type of research here. After that point, these things will flood right to the roof and flush out, and so you're getting this nice polished scalloping going on here. However, invariably in these things, you find yourself confronted with obstacles that are a grade up, okay? And there are several of them that I'll point out to you here. One is that the strata that you're following can take a minor hiccup. It can just be a concave bend that goes downward. The cave does not end. These are carved out by water moving through them. And the water that's moving through them then collects. You have the equivalent of a sump trap in a sink in your bathroom or something like that. And the question is, how long are those things? Well, in this particular case, we've been in this 450 meters so far at 30 meters depth. And the little sketch on the lower right was taken from the expedition base camp log that showed this guy had gone in with 2 tanks and a rebreather, took the rebreather off, took one of the tanks off, and was pushing the other tank ahead of him with a hammer trying to knock rocks out of the way. That's the kind of mentality that you have going on to explore these things. At the same time that was going on, there was another team that was saying, well, you know, if it stopped here going down, there's still a possibility that there can be multi-levels. These things are labyrinthine in nature. The rivers find their courses from higher levels to lower levels over time. And so this crew here on the, all these slides, started climbing above that underwater tunnel and in fact scaled 100 meters straight up using rock drills and Yosemite type climbing techniques to where they got to a point where the path onward was blocked with boulders in the ceiling. And the curious thing was that there was a lot of air coming out of these boulders. Now you had a choice there. You're hanging off 100 meters worth of rope over an underwater tunnel, and if you decide to pull one of these boulders out so that you can go past it, it may initiate a landslide, which then comes down and cuts all your ropes and might hurt you as well, or at the very least leave you stranded hanging on the wall up there. So we decided it was prudent at that point not to go any further. And so here was kind of a cross-section of what's going on in the bottom. That's a section view, and on the top is the plan view. There's about 12 kilometers of caves there. The parts that are blue and red are underwater. And that is not uncommon in a deep cave system to find the fact that a fair substantial amount is underwater. Some of it involves climbing going up. If we were exploring this from the top down, we would be throwing ropes down these shafts as opposed to climbing up from the bottom. But this is starting at the bottom of the problem and trying to see if we can explore into the mountain going upwards. Another thing that's rather curious, and I always found this funny when I looked at the history of exploration and things like that, is you would look at a map of a very deep cave over in France, for example, and it would have dates on it. 1898, 1930, 1952, These would be the places that over the course of time, sometimes over 100 years in many cases, there would be expansion of knowledge because technology had changed or something like that. And so many of these things will go for a 10-year or 15-year hiatus before somebody will say, you know, it's time to go back and look again. And so this right here, Cheve 2003, was the first expedition in 7 years to what is certainly one of the great caves of the world. It would be like the equivalent of Everest getting visited only once every 7 years. That's the nature of these places and the logistics of getting to them. This picture right here is rather curious. You can see all these little white streaks there. That's 3,000 meters of 9mm nylon line that's going to be used to rig this cave. And straightening it out and cutting it and bagging and things like that is one of the first little chores that you do on an expedition. The area is located just to the east of the well-known Tehuacan Valley. This is the place where corn was first discovered by anthropologists back in the 1960s. Proven to have existed there as one of the earlier agricultural remnants of society, ancient society. That was where it was first cultivated, I should say. This is Robert McNeish and that crew. In any event, you're going up from a desert through deciduous and then finally up into a pine forest at 3,000 meters elevation. And one of the things you can see here is what looks to be a giant valley. In fact, that valley extends in 5 different directions of about the same size, and sitting at the very bottom is this little soccer field with nice green grass going in the bottom. It's called a llano in Spanish, meaning meadow. And the curious thing about it is that this is up at 3,000 meters elevation. All the water that drains within that 5-kilometer diameter circle goes into this entrance right here. And when you find things like this is the kind of things that people who are looking to discover a deep cave somewhere in the world look for, those kind of signs. Does it capture a lot of water? Is it very high elevation? And in this particular case, it's really sitting on top. So what we saw before there was explorations in this thing called the Cheve Resurgence down at the very base of the mountain. We're now at the very far upper right at the entrance of Cueva Cheve, trying to go down. And in this year, 2003, the deepest point in the cave was 1,386 meters, and you see this thing called Cheve Sump. That means there's an underwater tunnel there. And as soon as you start adding all of the rope work and the fact that you got to do cave diving at the end of this, you start to see that the logistics start to mount up, which is why people don't do this every year. Very typical here. This is just going through a series of 120 shafts on the way down and traverses. They vary in size. Most of them, probably 15, 20, 30 meters. A lot of them can get up as high as 50 to 150 meters. This is at 320 meter level. I hope everybody understands metric, because I'm not going back to feet. We made that conversion a long time ago at the National Lab. And anyway, so this is the 500 meter level here. This is where pretty much the limit of where you could get on a single day's travel. This would be about a 24-hour journey to get out to this point and back out with a backpack. That's the beginning of a shaft. If any of you guys or people saw, for example, some of the Hollywood representations of what happens underground and things like that, invariably they have something like a bottomless pit, and they throw a rock in and it goes forever. Curiously enough, this one here is 150 meters. Okay, if you throw a rock down this, it takes about 6 seconds free fall to hit the bottom. That's really not much. The current knowledge of this kind of thing, a single drop, not necessarily the deepest cave in the world, but a single drop is now 600 meters over in Croatia. For people who are into morphological features, it is, as far as I've heard from colleagues, a straight drop. It's got alpine ice water that flows into it, so it's not a very pleasant place. But 2,000 feet straight down. Oops, slipped. Yeah, you're supposed to catch me here. One of the things about deep caves is that they are very much like a. To give you an analogy, it's like the limbs of a tree. Very high up in the tree, you have very small limbs. They come down and they eventually join to form a trunk. Think of each one of those things as a potential entrance that collects water. So the tops of a very deep cave frequently tend to be small unless they have a big focus mechanism. That's the term for that big sinkhole that you saw there. Frequently you don't have that, so you end up with these very tiny passages that as you get deeper, they get bigger after they join with another and another and another. But eventually, in all these cases, by the time you get to somewhere around the 800 to 1,000 meter level, you have a substantial underground river that you're dealing with that continues to build and become a danger, a physical danger. So you find yourself building tension traverses and things like that to bypass all this stuff.
This is the dry season, by the way, right?
That is correct. Yeah. Rainy season, that water would probably be 4 to 5 meters higher in that area, and you would not want to be there. Some passages would flood completely shut. This picture on the left here is something that's called a taut line slack line traverse, and it's a technique that we picked up from the Europeans probably 10 years ago, in which you have a what used to be called a Tyrolean line, which is a diagonal line going down, and then you have a slack rappel line, and so you hook a short cable onto the taut line, and you rappel the slack line. What it does is it carries you magically away from the place you want to avoid, which in this case is that big waterfall. And coming back up is a little more complicated. You have to put a pulley on the taut line and ascend the slack line. This kind of gives you an idea for the logistics here. You'll note that there's distinctly different types of suits going on here. That's because we've got 9 nations involved on these projects, typically sometimes 10 or 11. Right now it's mostly US, Mexico, England, France, Switzerland, Germany, Poland, Canada, Australia, Portugal, Spain are the main ones. These guys right here with the light colored yellow suits are all the Polish team. They're unloading tackle at Camp 2 at minus 800 meters. On the far right over there, the guy in the sleeping bag is on the lead rigging team. He's out about 2 days from the entrance at that point. These guys up there have just bought in a resupply of rope. and food to keep the lead team going.
My questions?
Yeah, sure. Go right
What's the
ahead.
communication? How does the guy who's 2 days on the lead? I mean, he's not using his cell phone.
No, that's a very good question. In fact, up until I would say last year, we did it all by basically messenger. You would send a message back with somebody from camp to camp to camp, which offered tremendous. It's like one of these games where you all sit in a circle and you tell a message to the next guy, and by the time you get back, it's not anything close to what this guy really wanted. And if it happened to be that he wanted a battery pack for a drill because they weren't going to be able to rig anymore, and what came out was, I need a charger for a battery pack, but it doesn't work with that one, and so the guy gets this charger for the battery pack and says, well, this only runs on 110 AC, we don't have that down here. And we've seen stuff like that, and that's a really good question because it bears on what I'm going to show you at the very end of this thing. It's this logistical pyramid that you're fighting, and the question is, can you cut the ties to the surface? Okay, and there are some things that you can cut, some you can't. But the issue of communication is one that was dealt with over the last year, and we had 3 solutions, one of which was to deal with magnetic induction radio and actually put receiver stations on the surface and then standard radio relays back. The second one was to run a multi-hop internet in, and the third one, which we ultimately ended up doing, was using a single wire low impedance comm system that used the earth as the ground. Very clever design, came out of Australia. It's just a little tiny box the size of a pack of cigarettes. And with that, you got one hand on the wall for your ground, and you press the button, and you've got communications, and it works like gangbusters. So we've been using that since. We ran 7 kilometers of wire over the last year in one system here. But anyways, this is a typical large tunnel when you're down there. Everybody asks me, what is it? Yeah.
While you're taking questions, you mentioned GPS system before. You wouldn't be talking to satellites either. What's the technology?
GPS would not work underground. I mean, you put a piece of paper over.
You said you used it to measure depth.
Oh, only between the open entrances. So you could go from the highest entrance to the springs, provided you had made a link between them, and it would serve as a corrector, an ultimate absolute corrector to whatever survey that you had done in between. Okay. It only works if you have access to open entrances.
How do you measure the depth then?
Okay, we survey in polar coordinates. You have a metric fiberglass tape. You have 2 optical instruments, handheld. These are Suntos, made in Finland. 1/4 degree accuracy on compass angle and roughly the same on vertical inclination. So if you think about it, in a polar coordinate system, you got all the information you need to convert back to Cartesian or standard GPS type coordinates. So that's basically how we do it. As you'll see here at the end here, we actually have a computer model of the entire internal coordinates of the mountain, and they're done in northeasting and up standard UTM GPS coordinates. So you could actually overlay those on a standard GIS model and look at it. Right now we're in the process of converting and getting the digital terrain model for Oaxaca, and I don't have it to show you. But you can see what the surface looks like on Google Earth. I could give you the coordinates. Anyways, one of the things that people always ask us here is, what does it take to get on one of these teams? And so the guy on the right over there is doing the normal test that we ask everybody to perform. So onward you go from camp to camp. It takes roughly 1 day's travel, and by 1 day's travel, we're talking anywhere from 12 to 16 hours one-way travel time between camps. So this is Camp 3. You're down at the 1,025 meter level, and you can get an idea for the feel of the tunnel right there. We're on the side of that on a little pocket over there. Finding flat spaces is always a challenge in a deep system because you have rivers that are flooding the place out every year. Yeah.
Are these strictly like exploration and surveying teams, or is there like a biological aspect to any of the exploration?
It is not uncommon to have a biologist along. It is not an intentional search that we do to have a biologist along in the same way that we would not necessarily have a geologist along. Most of the people who do this long enough recognize instantly if there's something unusual, and they'll frequently collect it. Some people just carry a little vial of formaldehyde because there are people who do this. You have to watch that though, because you're crossing a curious boundary in certain countries, and Mexico is one of them. If you're doing scientific research, you have to have a scientific visa, which is totally different from a standard tourist visa, which is what most explorers go on.
So a lot of the teams that are working on searching for life in Europa are looking at places that are sort of like void of sun.
Okay, that's an interesting connection you make there. Yes, people like Penny Boston and a few of these other people who are fairly well-known extremophile biologists and things like that, Norm Pace, John Spear, people like that. Some of the times they're finding these things in caves. Frequently they're finding them elsewhere in hot springs and places like that. There are a whole host of those, and that's a totally different talk. I will talk a little bit about the types of things that we're designing apparatus to detect on Europa when we do the 1230 talk. So again, the thing is when you're going down there, you're picking up more water all the way, which means you're constantly rigging more rope. So about this point, you've run out of your 3,000 meters of rope, and you're getting ready to move on to doing the final bits of exploration. And as we invariably find, the deeper you get, it seems like the higher the probability is that you're going to find a tunnel that is completely underwater. And so in Cheve, you're now at a point where you can see the water is building up massively in that left-hand slide. Still doesn't mean that you can't hit small spots. If you hit a hard layer of rock, you can easily hit a fissure that's narrow. That's actually not narrow. Narrow would be something that would be compressing, your chest and your back at the same time and just barely getting through. And so, this is the typical place that you would get up until probably 1970, 75. These places used to be called terminal sumps or terminal siphons, meaning that's it. Okay, that's the end. Let's get out. We'll de-rig the ropes and go home. Until people started taking a dive mask along and sticking their head underwater and saying, hey, the cave doesn't end here. It's just full of water, man. And so that started a whole cascade over the last 30 years of this skill, sport, whatever you want to call it, called cave diving. And it's developed into two distinctly different factions. If you go, for example, down to Cancun or the Yucatan, you can actually take a sport course and do a cave dive down there right now. If you have you can get an open water certification, then you do a basic cave dive. And you'll see what some of these cenotes and things like that look like. Very fascinating. Also very deadly if you go much further without the proper skills. The other faction, which is perhaps, I would say, on the order of one of them to 300 or 400 of these other types who go and visit these springs and things like that doing cave diving, is what you would see the divers who would do this kind of stuff. And the problem is that you have to have all these other skills behind you to get to these locations. The other problem is that to transport normal diving apparatus, let's say a tank of compressed air to these places, is enormous. And so when you get down there, if you don't find the way on the first crack, you've just shot all of your equipment, and all of it has to go all the way back up. Right now, this is at a point 8 kilometers from the entrance, one way, 3.5 days travel time, very arduous. That's after it's rigged. So you're about 6 weeks into the expedition right now just to get to this point, and that's with your one shot, right? So to break that, what people have done is gone to closed cycle life support systems, what are now becoming popularly known as rebreathers. And what those things do is close the metabolic loop, and you can get anywhere from 6 to 12 hours out of a backpack that weighs the same amount as what you had before, and you can take the recharge materials to give you another 12 hours. So suddenly the distance underwater becomes less and less important as long as it's not too deep. So in 2003, we were successful in passing this first one here. It was 120 meters long, about 12 meters deep, which by diving standards is not much. The second one, about 1 kilometer away, this was all a large cascade canyon, again with all that water that you saw before. 280 meter dive there, and on the far end of that, there was a place where the ceiling had collapsed, and you couldn't go any further. So the problem then is, now what do you do, right? Well, you could perhaps put a team out there and camp on that far side of that second underwater tunnel and see if you can weasel your way through. What everybody thought was, maybe it's time to start looking for an alternative way into the heart of the mountain. And so a year later, we had a 3-month reconnaissance expedition looking at areas in between that entrance and the resurgence to try to find a way on. And this is kind of a topographic map of what's going on. This is the main Cheve entrance right here. The resurgence is right at the very top there. That's over 18 kilometers straight line distance between those two. The limestone band runs as a 5 kilometer wide chunk, perhaps about that wide, from here to there. And the idea then is, can you find places where there are entrances dropping in? Well, this was one of the areas right here that seemed most profitable for looking for new entrances. And indeed, we found a lot of stuff while we were up there. It's one of the few remaining true cloud forests in Latin America. It's up at about 2,600 meters elevation. You can see everything is covered with green moss. This is on a typical day or untypical day where the sun is actually out. This is more typical, chopping your way through 10-meter high vegetation to look for entrances. But entrances we did find over 150 in the space of 3 months, and many of them quite spectacular from the entrance looking out and things like that. But ultimately, we ran across this one here, which had the name J2. Now, you might wonder where these names came from. Well, since we're doing the original exploration, in fact, the only people to ever have ventured into this cloud forest before were a handful of local hunters from this tiny remote village on the mountain down there called El Ocotal. And so this was pretty much cutting track where nobody had ever been, even in the jungle on that mountain. And we had various groups breaking up to go do the surveys. Well, the Americans went with a lot of the Mexicans, and we would put a P for pozo, which means pit in Spanish, and we were up to like P25 or 30, something like that. The Poles, the Spanish, and the Australians went off in another group, and they used the term J, which in Polish means jaskinie, which means cave. So J2 was cave number 2 in Polish, and that was where the name came from. Now, we were able to get down a little over 340 meters, something like that, during the course of that project. And the thing that made this very interesting was the fact that there was a wind blowing into this entrance that exceeded 35 miles an hour, 35, 40 miles an hour. And that alone was enough to drive a team to want to come back and find out where the heck that was going, because you don't get a wind that's 35 or 40 miles an hour in a cave unless there's something enormous underneath. It takes a huge hydrostatic differential in terms of compressed air to cause that kind of airflow to form, which also means that there's consequently a big cave, but a very deep cave as well attached to it. And so this is expedition life in the cloud forest. Gear is all hung under tarps because it's always dripping and rainy. Everybody hangs out in their tents when they're not up and caving. It is wet. It's dirty. You have to deal with a lot of really strange characters who have attitudes, and they have strange ways of resolving their problems. But in general, I would say, if I had to add up some of the experiences that I've had through life and what has been the most valuable to me, it's the people that you do these crazy things with. A lot of people I've talked to about this said, well, it's kind of like war. You're out there with a platoon or something like that. You all barely survive for some lucky reason, and you go back and you have that experience to think about for the rest of your life. The difference is here is we meet every year. This is my family. It's my international family here, and they've all got crazy ideas about what life is about and everything else. So it's a good cultural diversity time for all of us. So this is the exciting thing that got everybody to come back there. You might think that that's not so exciting, but in fact, in the first 400 meters really isn't exciting. In fact, it's really terrible. You're basically in a fissure. It's one of these deals where, unlike Cheve, it did not have a huge drainage area, and so therefore you were working at very high altitude. You're up in one of these tiny little limbs that's small and leading on downward. And ultimately, there's a series of shafts. There's one that's about 140 meters long. It's not nearly as big as the ones in Cheve, but is controlled by the same geological strata, so it tends to form shafts. Just like all the other things, repeating the ideas. Camp 1 was established at 500 meters, about 8 hours from the entrance. Not as far as normally we would like, but that was the only place that we could actually put a camp. Below that, you're now in clean washed rock. You're picking up streams. As soon as you have something about that size, you know you're going somewhere. You know that you're definitely headed for a very, very long, remote trip down into the core. These are kind of like walking through mountain streams and things like that with a slot canyon, but except having a roof over your head. You don't really even think about the fact that there's a roof over your head unless you're cave diving. That's a more disciplined type situation where you really are thinking about what are your options for getting out. Whereas here you got plenty of time to think about it. You get tired, you can just sit down. Same thing with being on rope. It's, again, J2, very similar to Cheve, 2.5 kilometers to get to the limit of exploration in 2005, 3.5 kilometers where we got to this year.
What's the temperature down at 700 meters?
It starts off at about 10 to 12 C at the entrance, and by the time you're down 700 meters, it's sitting at around 13, 14. And it's not so much from geothermal heating as from the fact that you get frost and snow and stuff like that at the high elevations that run down these valleys and dump into the entrance. And you're really equilibrating with the mountain by the time you get to that depth. So again, typical camp down there. We have a wonderful relationship with the Nalgene Labware company. And we've had it for almost 25 years, I would say. You might wonder, what do you use these things for? Well, the thing is, you're constantly in the rain, you're swimming, you're diving, you're doing everything. If you want to be happy underground, you don't want to arrive there with your food soaked, your clothes soaked, and your sleeping bag soaked. Very, very bad karma. Well, in this particular case, we found out a long time ago, actually, not that long ago, but we found a very good synthetic sleeping bag that would fit in a 4-liter bottle if you compressed it. Now, it takes some extra effort to make it fit in there, but it's worth it because these things are like nuclear indestructible. You can actually drop them down shafts and they just bounce around at the bottom and off they go. So you can carry your hammocks down there, you can carry your clothes down there in these things, and basically you're transporting these bottles through the cave until you get to where you're going to go.
Quick question.
Yeah.
I don't see any advertising, so how much does it cost and who's funding?
Very good question. I've run projects like this that have run as little as 25 grand to run an expedition when I was doing stuff in college at UT Austin, to as much as over 2 million. It depends a lot on the technology that's being involved. When we were first developing closed cycle life support systems, we were building 8, 9, 10 prototype devices that were running 50 to 80 grand a piece to small process manufacture. We had to design our own computers. That's a whole different talk that I don't have an opportunity, unfortunately, to get into here. But over the course of 15 years, we developed some pretty high technology, and building that stuff costs money. So I would say generally a project like this, you're looking at around 100 grand, and you've got roughly 40 to 50 people who are involved, typically on the order of 20, 25 industrial sponsors, corporate sponsors, to put up most of that. National Geographic has been very, very good to us. We have probably been sponsored by them, I would say, 7, 8 times. They don't always do a story. Once in a while they'll do a story in the Yellow magazine, the main one. Frequently they'll do stories in Adventure magazine, things like that. Sometimes it'll come out on the web. There's a great a website that's still archived there on the 2004 expedition. Rolex, another good sponsor there. But we've been very fortunate in the last couple of years to have had some individual patrons who put money into the, much like Lance Armstrong put up the, built up the U.S. cycling team for the Tour de France and all that. We had people who would put into a nonprofit corporation to try to get the team out in the field. And we've been pretty lucky the last couple of years. We've pretty much been self-sponsored for the last few years. That will change if we have another high-tech need that pops up. So somebody was asking how we know where we are. This is really typical. You have somebody who's a good artist, sketcher, who's taking the notes down, and basically you're building maps of what the roadway looks like ahead that you have to navigate through, and that's information that you pass on to the next crew that's coming in to change out with you when you want to go back to the surface. You might wonder, how long do you stay down? I've cumulatively spent 397 days below 400 meters deep. Typically, your run would be on the order of anywhere from 10 days to 2 weeks, maximum somewhere between 18 to 20 days. As you'll see when I show you the slide at the end here, we're extrapolating to complete this project probably on the order of 35 to 40 days as a mission length of time at distances over 30 kilometers from the entrance. In 2005, we had a rather curious thing happen that hadn't happened to me in 20 years, because invariably we always took cave diving equipment with us, just in the off chance that you ran into an underwater tunnel. Well, we had so much wind in this cave J2 that we figured, why bring diving gear? It's just an extra piece of stuff you're not going to use because there's so much wind. That means it's all open, it's deep, and we're just going to be rigging rope this year. So we had plenty of rope until we hit the 700 meter level, and you see this guy here on the left up to his armpits there in water in that fissure, which obviously he's not going to go any further in. And we didn't have any dive gear in base camp. So we backed up and we tried the old climbing trick. Go into the roof, see if you can find a place where the old river went, and try to bypass the sump. Well, we tried that for 2 weeks and it didn't work. And then finally we drew straws in base camp, and 4 lucky volunteers drove 2.5 days back to Brownsville, where a team from Austin, whom we contacted on sat phone, brought down enough dive gear for 4 people, and then they drove back. So within 5 days we had dive gear at camp. This is not your normal dive gear. These are carbon epoxy tanks. They run at 6,000 psi. They weigh about 8 pounds empty, about 16 pounds full. So there's half the weight of the tank is the gas that you're putting inside there.
And is that just compressed air?
Yes, in this particular case. Yeah, these are shallow dives, so you don't need heliox or anything else. That's a whole other subject we can talk about if people are interested.
So how was there so much wind if the cave was blocked with water?
Because there in fact were higher level fissures, but they were only a couple of centimeters wide. But because they're on the order of 30, 40, 50 meters tall, you've got enough cross section there for it to get through. However, even with that, what we discovered, and I'll show you something interesting here that happened just after this. In order to do a dive, you noticed how narrow that fissure was. Well, underwater, we found that in fact it was still almost that narrow. It was about a meter, less than a meter wide, maybe 3/4 of a meter wide. And you had to get through that. Well, the normal technique is to either have tanks on your back or on your side, but those wouldn't fit through. We couldn't get through the thing with that. So we ended up doing this thing where you strap 2 tanks together that's neutral, you push it ahead of you, and then you basically split through this tight crack underwater while pushing that gear ahead of you. And here's the phone we were talking about. The first use that we saw with that was in 2005, where we ran an underwater line through the underwater tunnel to talk to the crews who were on the other side, just in case we had a problem. So this went from Camp 2 to the crew that was on the lead team on the other side of the zone. And what they discovered over there was something really curious, and it's something that I haven't seen in 40 years of doing this stuff, is that where those guys are standing right there, there used to be a gigantic pile of boulders, about 15 to 20 tons worth. And they were small enough that they had backed up and gotten silt on them and built a dam which pulled the water up in this fissure to a point where you had to dive through. So they started pulling the rocks out, and they found that indeed they were lowering the water enough to eventually lower it 2.5 meters to where they had airspace to go through. So this guy right here on the right is actually coming through the place where we dived with those 2 tanks just the previous day. And beyond that, things are pretty much the same, just the kind of thing that you'd expect in a small infeeder into a gigantic cave system. Again, doing lots of rigging along the walls, and then finally you get to a fine point in the deep cavers world where you still have all this gigantic wind and you run out of rope at the end of some big shaft going down, and there's nothing but blackness below you. And then you come back and you see where the heck you are. And it's at that point that you begin the cycle anew for the next year's project. So everybody says, well, we're all out of time this year. What are we going to do next year? So you look at these things and you start thinking, well, are we coming back here or not? And in this particular case, we did. And again, this is the cultural diversity of the teams that we have up there. When you're sitting at base camp and doing nothing but either sitting in the rainforest or working in the muck, you tend to have a curious psychological outtake and look for ways to amuse yourself. This is Artur Novak on the left from Poland. That's Mark Wilson on the lower left over there from Australia, and Tony Dwyer from Germany on the right. And again, upper section, tight, narrow, dirty, uncomfortable. When you get down to about the 1,000-meter level, you're in the water. And this year we did a couple of things different this year because we were trying to experiment with ways to break this tide chain to the surface. And the first thing we did was try to reduce the amount of clothing that you have to take down. And one way we did that was by finding a way to introduce heat into the sleeping environment here. That's a silk tent, weighs about 1 pound, fits in one of those 4-liter Nalgene bottles, and it raises the temperature of 6 people sleeping in there by about 6 degrees C, 6 to 8 degrees C. It's quite significant, such that you can really cut down on the weight of what you're bringing on down. Again, typical camping environment here. Okay. So we are not in a gulag or a concentration camp here. These are happy explorers reducing weight. We've only got 1 spoon between the entire 4-person crew here. No bowls, no cups, 1 pot. And so that's you even think to the level of where you either don't take a toothbrush or you cut the toothbrush off to save the weight of the handle when you're going down to places like this, because everything has to be carried out. Here's another interesting experiment that went on. Probably half of the weight that we carry, this might be amusing or whatever, is the fact that we've gotten away from the traditional way that people used to use light underground, which was calcium carbide. Right up until about, I would say, 2001, 2002, this was the standard way that we went. Calcium carbide, you put it in a little container, you put water on it, it generates acetylene, You light the acetylene, you got this very bright flame. Anybody who's used a welding torch knows how bright acetylene is. They used this. It was invented back in the early 1800s for miners. We've now completely supplanted that. We used to use 700 to 800 pounds of carbide for an expedition. 700 to 800 pounds. We now use less than 20 pounds of lithium-ion batteries. And what you see right here are lithium-ion batteries that we've developed for drills. The way that you rig is using pneumatic impact drills. Well, those used to use really big, heavy batteries, and taking those out to the surface every time was probably 25% of the mass that you were transporting up and down. So what we did now is by going to these batteries and using a hydroelectric power station to recharge them by hanging in the water, we have snapped that tie to the surface. And off we go down into Big Tunnel. You're now at 6.5 kilometers distance from the entrance at about 1,100 meters down. Geology is all around. This is what's called a slicken side, for those who've ever heard that term in a geology class. It means a place where the earth has been just ripped up and down. You can probably see it out on the San Andreas Fault and other places like that if you look very carefully. But this is a graphic example where the left side has just dropped down below the right side, and you can see the signs of siliceous materials like clay and stuff like that, which have a nice color to them. That indicate the fact that these walls have moved to some seismic event in the past.
Also, we're seeing all these photos taken with a flash, and presumably you're seeing this whole thing with your Petzl headlamp, and that's about it, right?
Actually, not a Petzl headlamp. We design our own LED lights.
Okay, but with a Petzl band on them.
Yeah. No.
but so you're working on this with some cluster of LED lights.
Yeah. Okay. And
do like that,
right.
5 degrees of.
Right, and that's a good point. So if I go back up here, I don't want to delay the end of the show too long. If you look at a slide like this, okay, you don't see that when you're walking through it. Okay, that's a multi-flash thing. Pretty much like from about 5 slides before this until this right here, all those previous slides were taken with either bulb or large capacity underwater strobes and Kodachrome 200 film using Nikon OS5 cameras. This year, everybody has gone digital, and as a result of it, the quality has gone down. Okay, so we've gone from probably 20 megapixel, 25 megapixel resolution to these 3.5 megapixel waterproof cameras that you can put in your pocket. So everybody likes them, but we haven't crossed that frontier of bringing the quality back up in terms of digital, because I tell you, if you gave me the top of the line Nikon 15 megapixel digital camera right here, $6,000 camera, I and 39 other people on that team could trash it for you in less than a half a day in an environment like this. So that's the problem that we're still working on there. The environment can vary dramatically. The rock here can just be as fluted as Swiss cheese. You have to really watch yourself when you're walking on stuff like this. There's a term for it. It's called a kinoliths, means razor rock in Latin. And it's very peculiarly present in tropical caves in certain areas. This kind of looks like a pleasant area, but in fact everything they step on breaks off underneath them as they go through. Not everything is big. These are the kind of things that you occasionally have to deal with. And while you're doing that, of course, you're also passing 5 or 6 duffel bags that you carry between your team with them. Frequently we don't have the sense to show those in the pictures because they're in the way of the camera. We're down at the 1,150 meter level here. And finally, we've arrived at Camp 3. This is a far more arduous trip here. You're about 7.5 kilometers now from the entrance, 1,150 meters down. Same ideas again, though, the silk tent to keep you warm, lightweight stuff. There's our happy crew. This is the, we call this the Dus team. That's the Dutch members of our team on the left there, and myself and Matt Covington, who's from Stanford, are the US members, so it was the Dutch-US team. And this is a typical night down at Camp 3 again with the single pot servings. And it looks suspiciously comfortable in this place. But and in fact, you can have nightmares because you wake up and you go, oh, what a great place, and you step outside and realize where you are. And this is what you look like after 10 days down. It gets to be a little wearing on you. After about 20 days down, you don't look a whole lot different. You just have a little more facial hair. It just gets to be a place that you go to work. You get up every morning and do it. Again, things that you don't see on the surface, just razor-like little things with popcorn growing on them in the middle of a big tunnel, stuff like that. And of course, the ubiquitous underwater tunnel, which marked the end of this year's exploration at 1,210 meters down. That's our lead diver for this year, Jim Brown, coming back. This was not a rebreather dive. In order to get off a quick recon right at the very end of the trip, we just took 2 carbon tanks with us. And as a final act of arrogance, we tried to put a climb directly over the top of the sump, and so the conclusion of this story will leave you hanging, so to speak. So, where is all this going? You know, why do all these people spend enormous amounts of their private effort and money and time and risk their lives to do this? Well, it's largely because we're looking at something that's going to happen. It's going to be an event. It's going to be like, is the US or the Russians going to be the first on the moon? Once it's happened, that's it. It's history. It's gone. Right now, the deepest cave in the world is sitting out there waiting. There's a couple of people who think they have it. They quite likely do have it. Either the Russians or the US team probably are onto it. And Cheve, in the eyes of the American, conglomerate team, is the place where it's going to happen. And it probably will not be anywhere else in the world than southern Mexico, in our opinion. We may be surprised, but this is the way things have been going, starting as early as 1700. How deep people have been underground. Currently, this is a little bit out of date. The Russians hit 2140 as of January last year. Otherwise, the map is pretty much the same. Cheve is down there at number 9. You'll notice, however, that there's not a whole lot of difference between the top 10 in terms of vertical distance. If we were to find a 400-meter shaft at the end of Cheve, for example, we would surpass all that in one afternoon. I mean, it was just a matter of taking a 200-meter rope down there and another 200-meter rope, throw them, connect them together, rig them, and down you go. But it's always more arduous than that. This is giving you an idea. As of as late as 1980, you could count the number of 1,000-meter caves just the way you would the number of 8,000-meter peaks. So it was a very serious thing. Since then, the technology has changed. It's become a more popular sport. I want to close with one last PowerPoint slide here and then show you 2 other images. These are not all the same. When you say the deepest cave in the world at 2140 is sitting in Chechnya right now with the Russian team standing on top, was that as difficult as what's going on at Systematically, for example? Okay, if you look over here, Krubera, which is the place that was explored by the Russians. There's a great article in National Geographic May of last year, if anybody wants to read about what the Russians have been doing. Great guys, good work. But on the scale of things, you can see that what's going on down in southern Mexico absolutely dwarfs everything that's going on over there. The distances are enormous, what you're dealing with over here. Krubera, you can pretty much be at the bottom of Krubera in 2 days and that's it. And it's not going to go any deeper because the springs are at a level approximately 30 to 40 meters below that, and it's a very difficult piece of terrain in terms of strata that they'd have to get through to go that deep. So what I want to show you now, just in closing, okay, this is the vertical view now. This is Cueva Cheve. This is J2 out to what we did this year. There's another cave, Charco, and there's the resurgence. So you can kind of get an idea now. We're inside the mountain. And all these things are generally trending down in this direction. Ultimately, they're going to hit this area in here. And because you can see that they're getting close to it already, and there's a long distance here, what that means is there's going to be a lot of diving in that section right there. Not a very pleasant prospect, but it's waiting out there in the looms, which means we're going to have to invent better diving gear. Fortuitously, that is in the wind right now. We are working with a company to develop the Mark 6 rebreather. It's going to be about the size of a briefcase, give you 3 hours underwater at depths down to 60 meters. And that'll be out by January next year. Our team will start training with it for a 2008 push on the second sump in J2 down there. Now, from a logistics standpoint, okay, come back. Here we go. This is that topo map. What we've added now is this new piece of information here. Here is the work that's taken place over the last 3 years at J2. 3 months in the field this year, added this little tiny green line. Okay, now you start to get an appreciation for the scale of this kind of thing. I know a couple of really good people who have done high altitude mountaineering work, and I always ask them, what's it like? Like Ed Viesters, for example. We were having a conversation one time, and I said, when you go do Everest or K2 or something like that, what is the thing that really impresses you most? And he says, it's when you get to base camp and you look up and you go, holy smokes, this thing is huge, enormous. just bigger than anything you could possibly imagine by looking at a picture. Well, that's kind of how you start to feel after you go to a place like this and you say, oh man, that was a really tough expedition. We were down there for 3 months. We beat ourselves, all over the place. That's what we added. This is another thing. The difference between exploration and adventure is one word: data. If you don't bring data back, you haven't done anything. You've had an adventure, you've had a thrill, you've had some kind of a tourist trip or whatever. And some people, you really don't see that much in the deep caving world, but it's starting to happen in the mountaineering world with people going to Everest in particular, and you see the results of that with what happened, for example, in 1996. But in any event, all of this stuff in here in between is the giant unknown. How are you going to beat the Russians if you can't get into that? Well, this is the logistics map that we're projecting down. Each one of those little red circles represents a projected underground camp, 1 day travel time underground based on our knowledge of what's been going on in the system. We're expecting that there's a major fault that takes it all down to Mono, curving northeast and then finally northwest. But just to give you an idea, if you want to get to the resurgence from someplace like J2, which is currently the only open system that's down there, you're looking at 11 days one-way travel time to get to the bottom, 11 days back out. That's 22 days just to go down there and say hi, right? And then you normally will spend anywhere from 7 days to 2 weeks doing actual exploration. So we're looking at times of 35 days roughly when we finally pull this off. And God knows when that's going to be. The 2008 expedition is targeting right here, and if we're really lucky, we may get to 7D or 7U on that project. So that's where the world of very deep exploration into Earth is standing today. We could give you similar discussions over some of the other caves in Europe, but this is the kind of technology that's out there. This is what people are doing. Yeah?
How quickly, if at all, does the underground terrain change? Like you say 1 year you come back and suddenly one of the caves has collapsed. Is that common or not?
Almost not at all. We used to say that those are Hollywood theatrics to inject collapses into movies and things like that. If anybody had the bad karma of going and seeing that movie, The Cave, last year, they have an underwater collapse that traps this team, beyond it. But in fact, I know of at least 2 or 3 cases where that has happened, and it's usually been in places where it was virgin exploration. Nobody had ever been there before. The rocks were just precisely balanced at the wrong angles, and it's quite common, for example, to go through unexplored territory and step on a rock the size of a truck and have it just move like that, go back and forth. And it's really scary the first time it happens to you, but you realize, oh, well, it's not going anywhere. It's just balanced, But every once in a while, you have to think about those things. And one of the things that we do is when you have a team of 40 to 50, you come prepared for what we would refer to as self-rescue. So we have tools in there for dealing with that if we do have a collapse. Highly unlikely. I've never had to deal with one in 53 expeditions. But we had to deal with a lot of other stuff, including fatalities, broken bones, all kinds of stuff like that. Yeah?
What are you guys driving down there for food, like nutrition?
We've changed that dramatically. We used to go all freeze-dried, and then we went to the extreme of taking the freeze-dried, running it through a salad shooter, and compressing it with a jack into a 4-liter Nalgene bottle so that you get the absolute most dry food into the smallest possible place. What's happened in the last 2 years is that we said, this stuff really sucks. And it would be better to have something that is dense and dry. And so we've gone to doing things like high carbo routines. So for example, rice. We've gone back to whole grain rice, which is, I wouldn't have predicted this 20 years ago. We've done that. We go to ground dried meat. For anybody who's traveled in Mexico, there's a very popular breakfast dish called machacada, right? You can get machacada dry in Mexico at Sam's Club. And so this year we bought an 8-ton truck worth of food from Sam's Club and Soriana and a few other places in Oaxaca City, and we didn't buy a speck of freeze-dried food, and everybody actually liked it. It was pretty good. It was heavier, a little bit heavier, but everybody ate well, and it had a higher calorie diet than we've had in the past. We're burning about 8,000 calories a day, by the way, if anybody's wondering. It's on tour with the Tour de France.
Talking about logistics, you said you unstring the ropes, you take the pins out of the rocks, do you carry everything back?
No, it depends on where you're working. This is considered an active exploration project. So the things that will survive year to year, a stainless pot, for example, will stay at Camp 3, Camp 2, Camp 1. The ropes, if they can, will be pulled up to a location that is outside of the zone of the water rise. You can tell on the walls how far the water is going to rise. And you pull your ropes out of the main shafts, you coil them up, and you hang them. Stage them is the term that's used. And frequently we can just reuse them year after year. It saves on the order of 2 weeks of restocking effort. If you're going, when you're totally done with a place, if you're absolutely certain that it's done, you clean it. Everything comes out.
But at the end of the 2 weeks, you carry out your debris and your waste and all that.
All the debris comes out, all the waste, all the used, spent trash, anything like that all comes out. Frequently, if the sleeping bags and things like that are down there as utilities, we use common sleeping bags. People don't carry personal bags. So you go from camp to camp to camp. If they're wet or something like that and you're not going to dry them down there, you'll bring those out. Okay. If anybody has any other questions, you can hit me afterwards.